You are halfway through a complex code-based refactor. The logic is finally aligning, and then the system shuts you out. Limit reached. Professional developers on premium Claude Code tiers are hitting their API limits remarkably fast, sometimes draining a massive session allocation on a single basic task. The instinct is to assume a large language model treats its context window like a static hard drive. You drop a message in, and it stays stored locally while you add more instructions on top. But large language models possess absolutely zero persistent memory. To maintain a conversation, the engine must re-ingest and reread the entire session history from scratch every single time you press enter. This chart maps how the mechanism scales. X-axis, message number. Y-axis, cumulative token cost. It doesn't climb linearly. By message 30, it violently curves upward exponentially. Shading this area reveals a stark reality. 98.5% of tokens are spent strictly rereading old history. The solution requires abandoning the habit of treating an AI agent like a bottomless search engine. We have to architect high-efficiency command line interfaces to actively control this exponential curve. Maximizing output from advanced models is a strictly mathematical problem of rigorous token economics, not prompt engineering. The compounding math of the chat history is only the visible half of the equation. There is a massive volume of tokens consumed by the system before you even type your first prompt. Running a standard context command in a fresh zero-message session frequently reveals tens of thousands of preloaded tokens acting as immediate deadweight. This visual container represents your active working memory, and the heavy blocks filling it are the primary culprits of context bloat, Connected Model Context Protocol, or MCP servers. On every execution, these servers dump massive interlocking tool definitions directly into the model's context. A single connected MCP server can blindly force 18,000 invisible tokens into every single message in your loop, physically crushing the tiny space left for your actual instructions. The immediate architectural fix is strict lifecycle management. You must manually disconnect any unused MCP servers at the absolute start of every session. For permanent infrastructure, you should bypass MCPs entirely where possible. Default to native command line interfaces, like the Google Workspace CLI, which execute the exact same tasks without injecting heavy tool definitions into the context stream. This invisible overhead drains token budgets, but more critically, it mathematically suffocates the model by shrinking the space available for actual cognitive reasoning. Systems attempt to mitigate the processing of massive context blocks using prompt caching. But Claude's prompt cache operates under a strict 5-minute expiration window. As this digital timer ticks down to 0, the stored memory cache is instantly wiped. If you step away from the keyboard to debug a thought and return 6 minutes later, the very next execution must process your entire bloated history from scratch at full maximum cost. The financial drain is severe, but the performance penalty is worse. Heavily bloated context mathematically degrades the quality of the generated code. This deep U-shaped attention curve illustrates the loss in the middle phenomenon. Large language models pay very high attention to the beginning and the end of a massive prompt, but completely ignore the dense data buried deep in the center. To prevent this attention degradation, you must manually trigger context compaction commands the moment you hit 60% capacity, forcing the model to summarize its state before focus drops off. Unmanaged context enforces a double penalty. You pay maximum token prices to generate statistically worse code. Maintaining code quality while preserving tokens requires replacing chaotic, broad-spectrum searching with precision targeting. The assumption that unrestricted exploration yields better results is simply false. Granting an AI agent unrestricted access to freely explore an entire repository only multiplies your token waste. Look at this architectural comparison. The core function of your system prompt, the claude.md file, must act strictly as an index router, shown on the right, not a dumping ground for code and context, shown on the left. To prevent compounding the baseline read loop, the global markdown file is capped visually and functionally under a strict 200-line limit. Only highly specific data is permitted inside. Strict coding conventions, rigid behavioral rules, like requiring 95% confidence before executing a write command, and URL pointers to external documentation. From there, enforce surgical file mapping. Use precise file name pointers to route the model exclusively to necessary dependencies. Never command a broad exploratory sweep of a codebase. Architectural routing guarantees the model's attention remains violently focused on the specific problem, completely bypassing the exponential file bloat trap. The ultimate power user workflow involves orchestrating multi-agent systems to handle complex, sprawling codebase refactors. But spinning up these networks triggers a massive initialization penalty. As this visual indicates, deploying subagents costs roughly 7 to 10 times more tokens than running a standard single-agent session. Every new subagent wakes up completely isolated from the main thread. It is forced to instantly reload the full, heavy suite of system tools and context from zero. To control these costs, subagents must be restricted exclusively to isolated one-off tasks, like heavy data processing or deep repository research. Mitigating this crippling drain also requires strict multi-model routing. Delegate all sub-agent data processing to faster, lighter models like Haiku, while reserving Sonnet strictly as the baseline engine for actual codebase execution. The highest tier, Opus, must be locked down and deployed exclusively for deep architectural planning. Its high token weight has no place in the daily execution loop. True orchestration requires balancing the high cognitive leverage of autonomous agents against their mathematically destructive initialization costs. When perfectly architected, a highly optimized, frictionless system operates flawlessly at peak capacity, eliminating waste and keeping your entire workflow running continuously. The target operational state looks like this: minimal interface, a live command line status bar constantly tracking your exact model usage, token percentages, and context capacity boundaries in real time. Maintaining this real-time visibility over your context capacity is the strict prerequisite for the final layer of optimization, a self-updating architecture. You achieve this by embedding an applied learning block directly into your index routing file. When a system limitation is bypassed or a repeated error is solved, you instruct the agent to autonomously append a highly condensed 15-word rule to its own system prompt. This self-updating mechanism ensures the AI never wastes thousands of tokens processing the exact same mistake twice. It learns, and the cost of operation drops permanently. Eventually, even with perfect hygiene, the limit barrier will appear on your screen. If you have severed MCP bloat, built precise index routers, and enforced multimodal delegation, hitting the limit is no longer a failure of the system. Reaching the limit under a perfectly optimized multi-agent architecture is the ultimate proof that you are extracting maximum operational leverage from the tool. Engineering a leak-proof context engine scales human intellect without exhausting the machine's budget.